Yeah. Hello everyone. My name is Dharamveer Kumar and I'm a PhD candidate at IIT Bombay. And today I'll be solving assignment 3. And if you have any doubts, you can ask me now. Yeah, Kartike, go ahead. Yeah, okay. Okay. Yeah. Yeah, what do you mean? In which video lectures? Okay, in the class, what was told? Okay, so there is f, it's going from some interval of r to r. Now, not necessary, right? Just let me think. Not necessary. Oh, if f is continuous. Yeah, when f is continuous, yeah. Okay, think like this. For both closed and open, this is true. Uh, One second, yeah, let me think about it. That's an open mapping theorem. Continuous. So basically, for continuous function, what it means is if this is an open set, this is open. When f is continuous, this is a definition. Okay, so now you're saying that interval goes to interval. Yeah, I think that can be proven. Do you want me to prove it? Or like, can I do it after the assignment? Open, any open interval. Not interval, any open set. Not just interval, any open set. And inversely, that also means any closed set. Yeah, for open, it will be open. For closed, it will be closed. No. Interval is something like this. In R, whenever something like this is there or something like this is there. So whenever interval of okay, so I will tell you intervals of how many times. How many types? This is an interval. There are types of intervals. As one is like this. Sorry. And then only these like 3, 4, 5, 6, 7, 8. 8 type of intervals can be there. Interval means for every point x, like so on a real number a and b. So if this means instead of a, every point in A and B. So basically, if you want to write it as a set, X in R such that this is the set. This is neither open nor closed. This is an interval. This is called an open interval. This is called a closed interval. Okay? In this case, can you tell me what is this open or closed? What about the above? It is closed. What about this? No, this is called clopen. It's neither open nor closed. From this side it's open, from this side it's closed. So see the behavior of finite number and infinity over here. You have the same sign, it means the same thing, but this is closed. Similarly, this is open. In this side, that is not the case. That is the one difference between real number and infinity. Okay. The other things is, for example, when I'm talking about open set, general open set, this is an example of an open set. A general open set could be something like this: 1 to 2, union 5 to 9, union 15 to infinity. This whole thing is an open set. It's not an interval. Don't think of discontinuity. Think of interval like this. Interval means this. It has to be connected. And a set means a general stuff. This needs to be clear, right? Interval, and so interval does not exist in R2 or in higher dimensions. Open sets exist everywhere. All you need is a topology. Interval is a concept only on real number. Yeah, sure. So basically you have one question is, we'll address it later, that does continuous function maps an interval to a interval? Yeah. What is the next question? Okay. Yeah. So this is a set. If it is closed and compact, is closed and bounded, then it's compact. Yeah, for any set. It could be f of r, anywhere, like nothing, doesn't matter. If, as far as it's a set, it's the same thing. Okay, so we'll be solving assignment 3. Yeah, so this is a good question that also will clarify your doubt. It's a true and false question. If is a subset of R is open and closed, then A is an interval. Okay. This is a little tricky question, as I said, right? These are intervals. There are two things that we call interval, or if not, this form is R and phi. We call them as well interval because it satisfies for all x. There is no x in there, so like we also said, like if you define an interval, phi comes in that by definition. And again, R as well comes, like R is basically minus infinity to infinity. So if we did it in last class, if A is both open and closed, that implies A is phi or R. And this is an interval. These are in an interval. Hence, true. Let's do second question. Yeah. So whenever something is both open and closed, we did it in last class, it should be empty set. Other sets are either closed or open or nothing, or open or something else. Okay. Okay. Every subset of R which is countable. Like, it's countable means, first of all, it's discrete. Uncountable means, I told the second class, I guess, so it should map from natural numbers. So like natural numbers, odd numbers, even numbers, rational numbers, prime numbers, stuff like that. Okay, they're countable and compact. Must be finite. Okay, this statement is false. We'll give a counter example for this. It's a little non-intuitive. Okay, so if a subset of R is compact, implies it's closed and bounded. Now let's see. So you have to understand what bounded means very clearly. Okay, so for example, we say that it is bounded means it lies between a number. So like for some m to m, this set lies here. Okay, so it has to be compact and it has to be closed as well. And anyway, since it's countable, it's going to be discrete. Okay, all we need to make sure, if we want to give a infinite counter example, that if we start from, let's say, somewhere from 0 to 1, okay, and let's say if I start at 1 by 2, then 1 by 4, 1 by 3, 1 by 4, and so on. Okay, so if I give this set, this is discrete, this is going to be countable, right? One over n for n in natural number. This is by definition countable. For each number, there is a number over here. It's a set of x's. Okay, so basically it's a set x1, x2, x3, and so on. It is bounded because it is between 0 and 1. All we need, it is infinite. So if you want to give a counter example, this is infinite. all you need to make sure that it is closed, and there is 0 as well included in this. Start with 0. So all we need to make sure that this set is closed. When it is closed, it is bounded. So it is a compact set. It is countable, but it's not finite. So all we need to make sure that this 1 over n, where it is going, obviously it converges to 0, right? So all we need to make sure that it is closed. Then that's a counterexample, right? Now just 1 second now. Yeah. So now, if you want to understand this A set, right? This A is basically, if you want to write it in nice form, is 1 over n in z plus union 0. You're taking 0 as well. Okay. So what is R minus A? So whenever you want to show something closed, look at its complement. It will be what? Minus infinity to 0, union 1 to infinity, and the numbers between 0 and 1, like the intervals. So that will be what? You have to remove this stuff. So what you are doing? So in your interval, n was 1, 0 is there. Then what? 1 by 2 is there. So you have to remove this part. It's a complement, right? And these are included. So you have to remove. So from 1 to infinity is gone. You have to take an interval between this. So 1 by 2 to 1. Again 1 by 3. You want to take what over here? You want to take 1 by 2 to 1. 1 by 3 to 1 by 2. These all are the things that is not there in the set. These are the things exactly. So since now if you go to infinity, these things will be out, right? This is R of A. So this is A, this is R of A. A is again bounded. All you have to show it is closed, then it will be compact, and it is obviously countable. Now R of A, is it open or closed? So it is an arbitrary union of an open set. In last class I told you an arbitrary, see if you see over here, so we said that finite intersection of an open set is open, only finite. But for union, an arbitrary intersection of an open set is open. Arbitrary means it could be countable, it could be anything. This is open set, all the open sets, union of open sets, union of open sets, union of open sets. Hence, R of A is open. That implies A is closed. I'll give you proof actually. That will be better for you to understand that J belongs to some I. I may or may not be countable. It's some index. Okay. Actually, this is how you define open set, but yeah, right now we are like just defining it in terms of open sets. Yeah, like in terms of you know, we define open sets differently, and then we are saying this property also holds. One second. So I'm not sure if you are understanding. It's a collection of open sets. Like even it can be for like You can, I'm not enumerating it. Okay, it could be like literally anything. It doesn't have to be just natural numbers. Okay, for each real number, let's say you define an open set. For each real number, you can. Okay, that's totally fine. You cannot just enumerate it. We're not write it as, oh, 1 2 3, not like that. So yeah, so let's say it's an arbitrary. Let's just do for first I is countable, assume, and then we'll move forward from there. So this is there. You have to show that it's an open set, right? So what do? You take a point in this. That implies x is in all of OJs for all j, or some j. It is for some k in I. Okay, so if x is an open set, what does it mean? There exists an epsilon greater than 0 such that if this is contained in this, that implies yes. Okay, so what this means is, so if it's a union of open set, it will be in at least one of the open set. Once it is in one of the open set, how did I tell you that there exists an interval? So if there is x, let's say, and this is okay, right, some open set, and it is, this point is inside some open set, that means there exists, I'm not talking about open interval, I'm talking about it's in some open set. It could be something like this. There are other examples as well. I'm not giving you right now not to confuse you, but think of it as an interval. Okay, and now let's say it's inside an interval. There is an open interval that is contained within it. So if it is contained within this, it's also contained in the union. Anything is contained in something, it's contained if it is in union with something, and that's how you show that this ball is contained. Hence, and this interval, I'm writing it as a ball. You can call it a ball of radius epsilon. In higher dimension, that is how you write it down. But simple setting, you can write it as x plus epsilon, x minus epsilon. This is what ball of epsilon of x means actually. So this was the definition of open set, that there exists an epsilon such that this lies inside this, and then you can take again any arbitrary reunion. It doesn't have to be, you can define for each, let's say for each real number there is an open set. You can define that open set, right? For example, what you can do is for each real number x, you can define, so you can define x plus 1, x minus 1, sorry, x minus 1 to x plus 1 union for x in R. Okay, now if someone asks you what this is open. If I tell you this, you will just say, cannot say directly, okay? Cannot say directly. Is it empty? Could be empty. Is it closed? You don't know. You cannot say anything. But for this, you can directly say, this is R actually. This is nothing but R. But you don't need to find it in R. You can just say it's an arbitrary open union of an open set. So similarly over here. So that's how you solve the problem. Question 4, again true and false. The same logic what I told. Can you try to solve this? Same logic. Z is just a set of all integers. Try to find its complement. What is the complement of Z? You can write it in multiple ways. So you have to pick all the integers. The complement of all the integers. So you write R set minus Z is nothing but you're just leaving out integers. That's it. Again, this is an arbitrary, same logic. Arbitrary union of open set implies RZ is open. This implies Z is closed. Same logic applied everywhere. In true and false, there are no subsets which are neither bounded below Is this question clear or not? So basically they want to say that all subsets are bounded from above and below. This is false. I can give you multiple examples. Z R rational numbers, irrational numbers, R minus Z. These are all neither bounded from below or above. So it's a simple question. Assignment 3 is really easy. I hope you guys aced it. So question 5. Again, this be non-empty and P is in R such that P is the only limit point of A and P is not in A. So let's say A is a set, it's not an interval for now. So let A be a set and it's not empty and it's the only limit point of A. What is the definition of limit point? First of all, any limit point which is not in A, that means the set is not closed. So there are options that A is open, A is closed, A is both open and closed, and none of the above. So A is definitely not closed, so it cannot be both open and closed. Can it be open? Same counter example that we had earlier. It's another set A. Only limit point, whenever you say that there is only limit point, right? If it was not a discrete set, there could be multiple limit points. Okay, discrete means like these points. So if there is only one limit point, that means it's a discrete set. So now what is the set? 1/2, 1/3, blah blah blah. There is no 0 this time, because what is the limit point? You pick any sequence from here, any sequence. Okay. Limit point means it has to be a convergent sequence. Any sequence which converges over here, it in fact converges to 0. And 0 is not in A. That's why we are not including 0. Now this set, since first I told you, right, if something converges, right, if limit point is not in the set itself, it's not closed. Can it be open? So what is the complement? This time it's minus infinity to 0 is over here. This is not open. 0 is included in the complement in other open sets, and then union 1 to infinity. These are all open, but this is closed. This is not closed because there is an open set over here. This cannot be. So this is not open or closed, hence A is not open or closed. I hope you understand this. This is important. Containment definition of a limit point. It's a very simple thing. Just Google it if you don't understand, and then try to see what is the definition and properties. Not sure. Yeah. Basically, it's a general definition. It's a little difficult, but I will try to make you understand from. Oh, because this over here, okay. So you take a set A, okay. You can easily show how something is not open. For closed, you have to wait a little to understand. Okay. Now, if I take a point 1, okay, can I draw a ball around 1 or an interval around 1 so that it is contained in A? No, right? If I take 1 plus epsilon and 1 minus epsilon, no matter how small I do an epsilon, this will not be contained in A. So A is not open. Now for A to be closed, this has to be open Again, this cannot be open. If you take 0, for this to be open, so all these points are in an open set. It's very nice, it's an open interval. For 0, if you draw an interval, right, minus epsilon to epsilon, is it contained in R of A? No, right? Because no matter what epsilon is there, if you draw a line, this is 0. No matter what epsilon is here, there will be, again, we did a lemma, right? That 1 over, so basically for every real number, so 1 over epsilon is a real number, there exists a natural number. So for epsilon, there exists a natural number. So there is a natural number below this. Let's pick the biggest one. So 1 over, so just call it n plus 1 or n minus 1, something like this. So it will lie in this interval. So basically all the points, like this whole thing, is not contained in A because this is not in. Understand, like these points, no matter what epsilon you choose, this point is going to lie in there. So basically minus epsilon to epsilon, it has to be contained in this. Basically for 0, if you want to check if it's open at 0 or not, this should be contained in R of A. This side, from this side, yeah, definitely it's contained in minus infinity to 0. From this side there is a problem. Is the whole thing contained in some interval? Basically I'm asking, there is some epsilon over here, this is 0. This whole thing needs to be contained in one of these interval thing. Okay, so we know that there exists one n over here. Okay, take the biggest one nearest to it, and then there is 1 over n plus 1. And then there is, 1 over n minus 1, and then there is 1 over n plus 1. Right? So this point 1 over n basically belongs to minus epsilon to epsilon. It is inside this, right? And but this 1 over n does not belong to R over A. That means this is false. Hence, it's not an open set. Hello, Karthik, is this clear? Yeah. So by limit point, I'll just explain or give a bit of definition. It's called accumulation point, cluster point, everything of a set So if you want to understand a limit point, if there is a set, right, and there's a sequence in it. Then we have to take its convergence. Now, if you tell me what is the limit point of this? This set is also non-empty. 0 is definitely one of its limit point. It's not in A. Okay? It's not closed, not open. Does this satisfy this criteria? Is 0 the only limit point? No, because what I can do is very simply there is half, right? So I can do half plus 1 over n. For n greater than equal to 2. So the first point will be somewhere 1 by 4. If I do n equal to 1, it's going to be out of better greater than this. So 1 over 1 by 4. Sorry, if I do 2, it will be 1 actually, yeah. Then so on, so on, so on, so on, so on. This number, this sequence basically has a limit point of 1 by 2. This is what is called limit. You can have infinite limit points when there is an interval. And in general set, obviously you can have infinitely many limit points. But if you want a single limit point, you need to take this kind of discrete sequence, discrete set basically. So now next question is, again, it's a true or false question. Let A in R be, again, non-empty and bounded from above. Example, again, it's not saying bounded from below. It's negative integers. They are bounded from above by 0. They're non-empty. Negative real numbers, negative rational numbers, anything. So you define a set of, it's called minus A, set as minus A such that all A belongs to. This is negative of that. Then minus A is bounded from below and infimum of minus A is minus of supremum of A. For example, if I have minus of natural number, and if I do minus of that, that is natural number. Natural number is bounded from below. What is the infimum of negative natural numbers? If you include 0, it is 0. So both will be 0. Looks right. You need to prove it. So always go from example. If it looks right, go to prove it. Okay? So like, let M be upper bound of A. That implies this implies the minus A is an element of V. That's it. So hence minus m is lower bound of minus a, this set. So minus a is bounded from below. That implies minus a has an infimum. Okay. Now let alpha be, so A was bounded from above, so there has a supremum. Since that implies this is true, and I took arbitrary bound where m is upper bound of, is any upper bound of. Now let's call infimum of minus a is beta. Okay. Let alpha not equal to beta. So basically there's a set A, 0 could be anywhere, and you just flip this out. Showing in terms of interval, it could be anything, it could be a set as well. So if you flip it, it goes like this. Just flipping it in real life. Okay, so A, since A is supremum, this is true, right? That implies from here that V is greater than minus alpha for all V in minus A, right? That implies, so this is the lower bound, that implies that infimum of V, that is beta, is greater than equal to minus alpha. Okay, just flip this again around, that V is greater than beta, that implies A is this both implies that alpha plus beta is greater than equal to 0 and alpha plus beta is less than equal to 0. That implies alpha plus beta is equal to 0, hence alpha is equal to minus beta. What was alpha? Supremum of A minus infimum of minus A. Switch A to minus A. It is valid for any arbitrary set, right? This is also true. Question 7 is a bit lengthy. I'll do it later. Let's do simple ones first and then we'll move to that. So question 8. Which of the following is true? The question is R over Q is open. So over means like, sorry, set minus basically you can say, but not closed. So for R over Q to be open, sorry, R set minus Q to be open, Q has to be closed. So don't think about closed for now. So it is They are saying that it is not closed. That means the complement Q is not open. True, it is not closed. Okay, but is it open? For it to be open, will imply that Q is closed. Is Q closed or is R minus Q open? So basically, if you take, how do you write 0 and you take all the rational numbers? You cannot write it down, but yeah, 1, 2, and all the rational numbers. There are infinitely many rational numbers, a lot of rational numbers, and you just subtract them. How are you going to show that that set is open or not? It's a little tricky question. I'll tell you how. Another thing is, it is easy to show that it is not closed because the complement Q is not open for sure, right? If I take 2, if I take an epsilon ball, it is definitely not contained in Q, right? There will be an irrational number somewhere. So this is closed, but not open. I'll prove in multiple ways. One way is very simple. Whenever you want, between any two real number, there exists A not equal to B. Infinitely many rational numbers and infinitely many irrational numbers. Where over here infinite means countable. Obviously, there can only be countable because the overall rational numbers are countable. So it's anywhere between this is countable, and irrational, it's more than countable. You cannot map it to natural numbers, right? So what does it mean? So this, if this is the case, if you show this when you're done, right, that definitely if you take Q and if you take any Q in Q, and this is Q plus epsilon, this is Q minus epsilon, this is two rational numbers not equal, there will be an irrational number between them. So basically Q minus epsilon, Q plus epsilon is not contained in Q, hence Q is not open, implies RQ is not closed. If this were closed, that would be open. The closed thing is totally gone. Now you have to show that it is open or not. So if R over Q, if I pick an irrational number, for instance root 2. So if I do root 2 plus epsilon, root 2 minus epsilon, again there is going to be a irrational number between them. Sorry, rational number over here. There has to be a rational number because I said, right, between any two there are infinitely many rational and irrational. So this is gone. So always keep this in mind. I'll give you a more concrete solution, but always keep this in mind. Between two any real numbers there are infinitely countable rational numbers and infinitely many irrational numbers. Okay, so there is a more different example give you. So yeah, this is same example. They're giving a concrete example instead of a general example. So let's say you take any q. Okay, q belongs to rational and epsilon greater than 0. So there is any epsilon greater than 0, and you want, so what you're trying to show that q is not open. First we are trying to show q is not open. How do we show? Is q plus epsilon and there is q minus epsilon. You have to show that this is not contained in q. How do we show this? Basically we are saying that there exists one irrational number between them. How do we show this? So what do you do is k plus and you want this to be less than epsilon. So that means for a given epsilon, so for a small enough epsilon, choose n such that if I choose n naught, then q plus root 2 over n for all n greater than n naught. This will lie over here. Okay, so a rational number plus root 2 over a natural number. Is this rational or irrational? So an irrational number multiplied by any natural number or a rational number is going to be irrational. And again, irrational plus rational is irrational. So hence, this whole sequence, is this right? This is a countable example. There could be any amount of numbers, irrational numbers. So this implies that q plus epsilon, q minus epsilon does not belong to q. Now that means q is not open. That means RQ is not closed. Now RQ is talking about is RQ open or not. One thing that is wrong, R minus Q is definitely non-empty, but it's not countable. Note that this is not countable. In one of this, in the, I think old solution or some solution, it was given countable. It's not countable. So in all likelihood, the same thing has to be done over here. You pick an irrational number, q bar, and you do q bar plus epsilon. Can you do something like this? Can you tell that there exists a irrational number, a rational number between them? for any arbitrary epsilon. So from here we show that bit if you take q to be epsilon to be some rational number, so between two rational number there is an irrational number, right? We can choose epsilon to be anything. Okay, so we can choose one rational number. So there is root 2, so there is 1 over here. Okay, you don't have to do anything. All you need to do is 1 plus can we do that? 1 second, yeah, let me think. Basically what I'm saying is we can go closer and closer and closer and closer. Yeah, very simple example. Pick a set and define this set, right? All the rational numbers such that x square is less than equal to 2. Right, and maybe greater than 1. So what is the first rational number? What is the set? Like 1 belongs to A, definitely. Okay. What this means is that the limit point of A, basically root 2, is a limit point of A. Basically, if you take a sequence of all rational number, it converges to root 2. So basically, this is one thing. If we show, then what we know is that for every epsilon greater than 0, there exists n such that, say, we define it because q can be enumerated, it's countable, so we can do it xn. There exists n in natural numbers such that xn minus root 2 is bounded by epsilon. That implies xn is greater than root 2 minus epsilon. There is always a rational number. No matter what interval I choose, there is always a rational number in between. it's a roundabout thing actually. Basically, it all boils down from here. Between any two real numbers, there are infinitely and rational numbers and real numbers. Rational numbers. Yeah. Just 1 second. I'll just check if it's recording or not. Yeah. So we're back. The one example is what I can tell you is a very simple one. There is an irrational number. It's a q bar. There is q1 and q2. So what you do is you take average q3 as q1 plus q2 by 2. Okay, so let's say q3 lies over here without loss in generality. Then what you do, you take q1 plus q3 by 2 as q4. If q4 lies over here, you take q3, q4. If q4 lies over here, you do this. It will go infinite up to, that's a sequence. The sequence is such that this q bar is always contained between qn plus and qn. It is a bounded sequence. It's always converging. So basically what we can say is this in fact will actually converge to Q. There are a lot of things you can do from discussion actually to understand this part. Okay, so we will do question 9. Let me check if recording is on or not. Yeah, it is on. Yeah. Let whenever they say just open and close, don't assume interval. Assume it's a set. Which of the following is true? So whenever they say need not be open or something like that, it's not open. It doesn't mean close. Okay. So what are the options? it's an open set, just do it from example. Okay, so there's an take for example an interval. So you can exclude this from example. Let's say you take an open set 2 to 3 and a closed set, or 2 to 4 rather, and a closed set 3 to 5. Open, closed. Intervals are easy to understand, that's why we take interval, but they're not the same as the set. It could be more general. But if you give a one counter example, you can remove things. But if it's not valid for this, it's definitely not valid for more general sets. So let's say let's call it A. A is open and this B. So what is A slash B? It is definitely open. So A minus B is not closed. These two are. What about B minus A? It is 4 to 5. It's closed. But you cannot say, for one example, you cannot say it need not be closed. You cannot neglect that. So one of these two things. So if you're in the exam, don't worry about A minus B, just worry about B minus A and get done with it. But when you're outside the exam, you should focus on understanding the whole concept. Okay. So if B is closed and A is open. Okay. So if B is closed, this implies that right? What we want to see is what is B minus A, right? So how do you write this? Right? If there is A, okay, and similarly can you see why this is true? So you're removing all the points in R from A and only keeping B when you're intersecting. This is the same thing. Now this is closed. And since A is open, this is closed. Intersection of two closed set, intersection, and it's a finite intersection, that means it's closed. Actually, for closed, it's arbitrary, but yeah, it is closed. Okay? Similarly, you can do for A minus B, A intersection R minus B. Open, open, this is open. Question 10, last question. So consider these subsets. three sets. Which of following is true? So A, B, C are compact. A looks compact, right? It's closed. Union of closed is closed, and it's bounded definitely. A looks compact, right? But C is not. A is compact, but B and C are not compact. It's compact. This is definitely wrong. A is clearly, from here you can see it's compact. If we only show from here, if you look at the options, if B is not compact, you are done. In that case, only C will be the option. Okay? But we'll do all of them. So it is X in R, X greater than 0. So B is this bounded? No, right? Give me any number. There is a number in this, real number, right? So B is not bounded, implies not compact, done. Over here B is compact, over here B is compact, this is done. So B is not bounded, not compact. Is it closed? Just out of curiosity. It's basically B is nothing but 0 to infinity. Is it closed? What is its complement? This is open, hence this is closed. Closed but not bounded. What about C? A is clearly compact. So what about C? It says that C is also not compact, but why it is not compact? So C is X in 0 to 1 and X in R cube. So X is between 0 and 1, it's clearly bounded. The only reason it was not compact because it's not closed. So basically you are picking all the irrational number in 0 and 1. If this were closed, Q would have been bounded like so R minus C what is R minus C? Minus infinity to 0 first, then 1 to infinity, and then is this an open set? I take 0 for every point I need to show it's open. This as I told you, there is definitely an irrational number over here. We did that earlier. So that means minus epsilon to epsilon not contained in R minus C That implies RC is not open, C is not closed. Hence it is. Let's do question number 7. Let me write it down first. So, when we'll do this. This is going to take time. This question will take time. This last question. Okay. So let's Z plus. Basically, it is saying I can be empty. It is saying definitely I is non-empty, but it may or may not be closed. This will clear your doubt what is an interval and what is not. This is like very important. I is non-empty, closed interval. It's an intersection of closed sets. Arbitrary intersection of closed sets. If any one of them was empty, this would have been empty. So none of these intervals are empty. These are countable closed intervals, right? No matter what it is, it could be anything else. It's countable closed intervals. It's definitely closed. So this is not correct. Okay, for emptiness and everything we'll see, but it's definitely closed. Okay, so each are closed and bounded. So basically an and bn's are not infinity. Each of them are very nice individually. Not saying this could clearly be basically all rational numbers minus 1 plus 1. Each of them are closed, their intersection is non-empty, and we want this. What happens to this? The intersections. Okay, so for this part, we'll see what happens. Is I bounded? You pick a point x, it lies in all of the intervals. Since it lies in all of the interval, it lies in it, even if it lies in one of them, in each one of them it is bounded. So is it bounded? So basically, let's say you take a1 and b1, right? And these are finite. a1 b1 are real numbers, because since they are bounded they have to be real numbers, right? And x belongs to this a1 b1. That what does it imply? That x is bounded by something. So no matter what point you take, it's bounded by, take even one of the intervals, it's bounded by basically b1. So this whole I, basically b1 is upper bound of I. So is b2, so is b3. All of them are upper bound. Okay. Now let's define something called Jn, where what you are doing is taking the first n intervals, and when n goes to infinity, that's what I is. Okay. So since there is one more intersection, this will be definitely a subset of this. Right? For example, J1 is I1, J2 is, clearly you can see, right, J2 is a subset of J1, so on. right? This is definitely a subset. Clearly, like, as I said, I is bounded. Simply, these JNs are also bounded, right? They're bounded by nothing but B1. Okay. What is Jn plus 1 is nothing but Jn intersection An plus 1, Bn plus 1, or as we call it, In plus 1. Intersection of closed set, it's a closed set, this is closed. So Jn's are bounded and closed implies that Jn's are compact. And I is nothing but, if you take an intersection of Jn's, they're the same thing. It's an intersection of, arbitrary intersection of closed in this. That implies that I is definitely compact, closed and bounded as well. Not sure if it's an interval and it's non-empty and everything for now. Okay. If any of these intersections were phi, I would have been just phi. But none of the intersections are phi. So now, let's say if I1 was this, I2 was this, right? So J will be this thing, it's an intersection J2, right? Can the other thing be phi? So like now J2 intersection I3 be phi. For this to be phi, at least one of them, because J2 is also I1 intersection I3. So basically what it means is that these Jn's are not non-empty and are definitely an interval. These Jn's are interval, like for example J1 is just I1, J2 is, if you're taking an intersection of two intervals, it's not phi, that's an interval. Now you take another interval, again that has not to be phi, it will be over here, something like this. So I'm not talking about infinity right now, I'm talking about finite. This is an interval. Okay, so now so like for example, like over here I1 was interval, so you take Jn to be an interval from somewhere, right? In the next point, let uv belong to Jn plus 1, right? Such that without loss in generality, None of them are empty. Okay, and that's why I'm talking about equality. A and B can be equal, not saying they are distinct. And any W in R such that you pick these points. Right? And then UV belongs to this AN plus 1, BN plus 1. This implies W is in AN plus 1, BN plus 1 for sure. You know this, right? That Jn plus 1 was inside Jn. If UV belongs to Jn plus 1, UV belongs to Jn as well. So this implies that W belongs to Jn. This clear a bit? This is basically an induction. Suppose Jn is interval. If Jn plus 1 is interval and J1 is interval, this implies like you can say, yeah. So you start with someone, and if you show that the next one is an interval and the first one is definitely an interval, then so J1 is definitely an interval. This is true. All you have to show that if Jn is an interval, then Jn plus 1 is an interval. So basically, right, let's say you're assuming that Jn is an interval. It has some alpha, beta. Jn plus 1 is inside it. It may or may not be an interval, right? You have to prove that Jn plus 1 is an interval. So what is Jn plus 1? Jn plus 1 is nothing but Jn intersection, let's say this was an interval, of An plus 1, Bn plus 1. They cannot be non-empty. So definitely An plus 1 has to be less than or equal to beta. Otherwise that would be empty. Okay. When n plus 1 is beta, this is nothing but the singleton set. This is again an interval. And if an plus 1 is anywhere over here, this implies an plus 1 to beta. And if an plus 1 is over here, and again we need and right, since it's in intersection, bn can be anywhere, doesn't matter. Whenever bn plus 1 touches this less than, so if when bn plus 1 okay. So basically what they're saying is consider uv in an plus 1 bn plus 1. So this is very clear, right? So you basically very easily you can see that all of them are going to be just interval. So this implies that if Jn was an interval, Jn plus 1 is an interval, right? Hence, by induction, Jn's are interval. Still haven't done it for J infinity. So if Jn's are interval, and let's call it alpha and beta n, and since Jn plus 1 is inside Jn, that implies the alpha n is decreasing and beta n is, sorry, beta n is decreasing, alpha n is increasing. What does that mean? So there was like some alpha 1, beta 1, alpha 2, beta 2 inside this. So on a line, so this is alpha 1, this is beta 1, this is alpha 2, this is beta 2. Now alpha n, any n, it could, so because there is no non-empty thing, right? This is true. And also well, this alpha n is bounded from above, so this alpha n definitely converges. It's an increasing sequence which is bounded from above, so converges. And beta n also converges. So let alpha n converge to some alpha and beta n converge to some beta. since it's an increasing sequence, so like alpha 100, and then some place will be beta 100, and so on. So alpha is going in this direction, so it will always be contained. So basically alpha beta both are contained in Jn. It's coming down and down and down, and that implies so I is non-empty. So if you go over here, I is definitely non-empty. Is it in an interval? So from here we have alpha beta is contained in I, and is I contained in alpha beta? If we show this, we can show that I is equal to in fact alpha beta. It could happen that alpha can be equal to beta. You can define a set so that alpha can be equal to beta, and I is just a single point. How do we show this? That's the question. It's very, very simple question. All you have to show that is J, basically I, or like pick a point in I, it's a point in Jn, pick x in I, all Jn's, and it's intersecting to, it belongs to the infinity one. So this is true. I'll just handle one question. You were saying so basically if you have an interval, if the function is continuous, the range will be interval. So now this was the question, right, Karthika? So let f of I be a subset in R. I is something like this. So this is just f of a, an interval. But when I is not something like this, I is something, an interval like a to b or something like this, or a to infinity, anything, not a single system. We can pick 2 points in that, definitely. Okay. So since we can pick 2 points, suppose, so that's why I cleared a case when it has just 1 point. Okay. Suppose y1, y2 belongs to f of I. And let lambda in R be such that lambda is in now consider S to be x in I such that, so you're taking from lambda, we're just picking any 2 points, arbitrary, okay, in f of I. There exists a 2 point, okay. There may not exist 2 point, there can be just 1 point, everything is pointing to 1. Then it's an interval, definitely an interval. So when if f of I is only 1 point, it is an interval. So pick not equal to y2. Okay. And you pick another set since y1 exists, right? Since both are non-empty, moreover, they're picking all the points, right? Right? S union T is whole of I. So this is like this. So there's an interval divided into two parts, both are non-empty. Yeah. So from here on, basically you use the continuity. So now if you do first f of s and f of t, and then what you do is you check a continuity of maps, as I told you, right? Open set, if you take inverse, maps to open set. A closed set is maps to a closed set, only the inverse. So now you, from here, you need to get to the inverse of it. So I'll do it in next class. The time is up now. So I'll do this next class and I'll explain it to you. Okay? I think